In 2003, NASA pointed the Hubble Space Telescope at a patch of sky so small it could be hidden behind a grain of sand held at arm's length. The telescope stared into that darkness for 11 full days. What came back was not emptiness, it was 10,000 galaxies. Every blurred shape in that image was an entire galaxy containing hundreds of billions of stars, and that tiny patch of sky was considered empty before Hubble looked closely enough. Today, astronomers estimate the observable universe contains roughly 2 trillion galaxies, and every single one of them is moving away from every other one. Not because galaxies are flying outward through space like debris from an explosion, because space itself is stretching. The distance between galaxies is increasing everywhere at once. There is no central point where the expansion began. Every observer in the universe sees distant galaxies receding in all directions, as though they themselves are standing at the center, which leads to one of the most unsettling questions in modern physics. If the universe is getting bigger, what is it getting bigger inside of? Human intuition immediately reaches for an answer. There must be some larger emptiness outside the universe, some endless black backdrop the cosmos is expanding into. But according to modern cosmology, that backdrop does not exist. There is no outer space outside the universe, no hidden void beyond the edge, no surrounding darkness waiting beyond the galaxies. And somehow, the universe still expands. This creates a contradiction so difficult for the human mind to accept that even trained physicists struggle to describe it without relying on metaphors that quietly break down under scrutiny. If the universe has no edge, how can it grow? If space itself is stretching, what exactly is stretching? Did anything exist before the Big Bang, or did space itself begin there? And if the observable universe is only the part we can see, how much larger is the real universe beyond it? This channel grows because of people who take a moment to like and subscribe. If you enjoy these late night journeys through space and physics, thank you for helping the channel keep going. Now, let's begin with the distinction that changes this entire question: the difference between the observable universe and the universe itself. Imagine drifting outward forever, past every galaxy visible in the night sky, past every cluster mapped by telescopes, past the faintest points of light ever captured by Hubble or James Webb. At some unimaginable distance, you would reach a limit, not a wall, not a barrier, just darkness beyond your ability to receive information. This is the first distinction we need to hold on to carefully. There are really two universes in cosmology. People often merge them together without noticing, but they are not the same thing. The observable universe is everything whose light has had enough time to reach us since the beginning of cosmic expansion, roughly 13.8 billion years ago. But because space itself has stretched during that journey, the edge of what we can currently observe is not 13.8 billion light years away. It is about 46.5 billion light years in every direction. That number surprises almost everyone. Light traveled for 13.8 billion years, yet the source is now vastly farther away because the fabric between us and that light expanded while the photons crossed it. Space changed during the trip, quietly, constantly, but the observable universe is not the entire cosmos. It is only the portion visible from our position at this moment in cosmic history. Beyond that horizon, the universe almost certainly continues. More galaxies, more stars, more darkness between them, the same laws of physics unfolding where we cannot see. The cosmic horizon is therefore not a physical edge, it is an information limit. Beyond it, light simply has not arrived yet. Standing at that horizon is like standing in deep fog at sea. The fog does not mean the ocean ends, it means your vision does. This changes the expansion question immediately. When most people imagine the universe expanding, they picture a growing sphere surrounded by emptiness, as though galaxies are rushing outward into a larger void. But that mental image quietly assumes the observable universe is the whole universe, with a physical boundary enclosing it. Modern cosmology does not describe reality that way. The full universe may be vastly larger than the observable region. It may even be infinite. And if space is already infinite, there is no outer edge advancing into anything else. To make this easier to picture, cosmologists often use the balloon analogy. Imagine tiny dots drawn across the surface of a rubber balloon. The dots are galaxies. The rubber surface is space itself. As the balloon inflates, every dot moves away from every other dot. No dot is the center. Every location sees expansion happening around it. But the crucial detail is usually missed. The universe in this analogy is the two-dimensional surface, not the air-filled interior. The interior does not represent hidden physical space. It is not part of the model at all. Hold on to that discomfort for a moment. If the balloon expands, we instinctively ask what lies inside it. Yet in cosmology, that instinct may be leading us in the wrong direction entirely. In the early 1920s, the universe still seemed comfortably still. Astronomers debated the nature of spiral nebulae. Einstein's equations had transformed gravity forever, and most physicists assumed the cosmos itself was eternal and unchanging. Then a young Russian mathematician began rearranging the equations. Alexander Friedman worked in Petrograd during a period of political upheaval and famine, far from the major scientific centers of Europe. In 1922, he sat down with Einstein's general relativity, the theory describing gravity as the curvature of spacetime, and asked a dangerous question. What if the universe did not remain fixed over time? Einstein himself had resisted that possibility. His equations naturally predicted motion on cosmic scales. Gravity should pull matter together, causing the universe either to collapse inward or expand outward. But Einstein found this deeply unsettling. A changing universe felt unstable and unrealistic. So he inserted an additional mathematical term called the cosmological constant, a value designed specifically to counterbalance gravity and hold the cosmos perfectly still. Friedman removed it. What emerged from the mathematics was startlingly simple. A universe filled with matter could not remain static forever. The equations demanded motion. Space itself had to either contract or expand. There was no stable middle ground. Einstein initially rejected Friedman's work, claiming the calculations were physically meaningless. But the mathematics was correct. Quietly, the idea survived. 5 years later, in 1927, a Belgian physicist and Catholic priest named Georges Lemaitre arrived at the same conclusion independently. But Lemaitre took the logic one step further. If the universe was expanding now, then reversing time would compress everything closer together. Far enough back, all matter and energy would converge into an unimaginably dense state. He called it the primeval atom. This was the first real scientific version of what later became known as the Big Bang Theory. Not an explosion in space, but a transformation of space itself from a denser, earlier condition. Einstein met Lemaitre at a scientific conference and reportedly delivered a brutal response. Your calculations are correct, he told him, but your physics is abominable. But the sky was already siding with Lemaitre at Mount Wilson Observatory in California. Edwin Hubble had been measuring distant galaxies using the newly completed 100-inch Hooker telescope. In 1929, he published a result that changed cosmology permanently. Galaxies were moving away from us, and the farther away they were, the faster they receded. The relationship was precise. Distance and recession speed rose together almost perfectly, exactly as an expanding universe predicted. Einstein later visited Mount Wilson and saw the evidence firsthand. The static cosmos he had defended no longer survived observation. He publicly accepted expansion and later referred to the cosmological constant as the greatest blunder of his career. But history twisted strangely afterward. That discarded constant returned decades later as the leading explanation for dark energy, the mysterious force accelerating cosmic expansion today. And beneath all of it sat Friedman's deeper insight. The equations never described galaxies flying through empty space like debris from an explosion. They described space itself changing scale over time. Every distance in the universe stretches together, all at once, because the geometry underneath reality evolves continuously. Long before we could measure the size of the cosmos, we learned how to read the language hidden inside light. Every chemical element leaves a distinct pattern when light passes through it. Hydrogen produces one arrangement of lines, helium produces another, sodium, oxygen, calcium, iron. Each writes its own signature into the spectrum, the spread of light separated into wavelengths like a rainbow through glass. These patterns never change. A hydrogen atom in a distant galaxy behaves exactly like hydrogen in a laboratory on Earth. That constancy gave astronomers an extraordinary tool. By comparing known spectral lines with the light arriving from distant objects, they could detect motion across enormous distances. Something strange appeared almost immediately. When an object moves away, its wavelengths stretch slightly longer, shifting toward the red end of the spectrum. This effect is called redshift. The faster the recession, the greater the shift becomes. Between 1912 and 1925, American astronomer Vesto Slipher measured these shifts in spiral nebulae, cloudy structures whose true nature remained uncertain at the time. Working patiently at Lowell Observatory in Arizona, he found that nearly all of them were receding at immense speeds, sometimes more than 1,000 kilometers per second. He did not yet know they were galaxies. He only knew the universe seemed restless. Then Edwin Hubble entered the story, using Cepheid variable stars, stars whose brightness changes in a predictable cycle. He measured distances to those same objects with unprecedented accuracy. When Hubble combined his distances with Slipher's velocity data, a simple relationship emerged from the numbers. The farther away a galaxy was, the faster it receded. Double the distance, roughly double the speed. This became Hubble's law, one of the foundational discoveries of modern cosmology. Today, the expansion rate is described by the Hubble constant, currently measured near 70 kilometers per second per megaparsec. A megaparsec equals roughly 3.26 million light years. Every additional megaparsec of distance adds another 70 kilometers per second of recession speed. But something deeper was hiding beneath the measurements. At first glance, redshift resembles the ordinary Doppler effect, the familiar stretching of sound from a passing siren. Yet cosmological redshift works differently. Galaxies are not simply racing through pre-existing emptiness. The light itself stretches because the space it travels through stretches during the journey. The wavelength expands with the universe. That distinction changes everything. If galaxies moved through fixed space, asking what lies beyond the expanding universe would feel natural. Motion usually happens inside something larger, but the observations increasingly suggested that space itself was evolving dynamically beneath all matter and light. Even the most distant objects reveal this process. One of the farthest galaxies ever observed, GNZ 11, emitted the light we now detect when the universe was only about 400 million years old. The galaxy itself is currently estimated around 32 billion light years away because expansion continued while its light crossed the cosmos. The photons kept traveling toward us. Space kept stretching beneath them the entire time. For a long time, the expanding universe appeared elegant but incomplete. The equations worked beautifully. The galaxies receded exactly as expected, yet several deep contradictions remained hidden underneath the model, like cracks beneath ice. One contradiction filled the entire sky: the cosmic microwave background, the faint radiation left from the early universe, arrives from every direction with almost exactly the same temperature, about 2.725 Kelvin. The differences are astonishingly small, roughly 1 part in 100,000. That smoothness should not exist. Regions on opposite sides of the observable universe are separated today by around 93 billion light years. According to the standard expansion model alone, there was never enough time for those regions to exchange energy or information before the light began traveling toward us. Yet somehow they settled to nearly identical conditions. Another problem emerged from geometry. Einstein's equations predicted that any slight curvature in the early universe should grow dramatically over billions of years. Even a tiny imbalance should have produced a cosmos visibly warped by now. But every major measurement showed space remained extraordinarily flat, accurate within less than 0.5%. Then particle physics introduced a third issue. Several grand unified theories predicted huge numbers of magnetic monopoles in the young universe, hypothetical particles carrying isolated magnetic charge, a single north pole, or a single south pole. Cosmologists expected them everywhere. None were found. In 1980, physicist Alan Guth proposed a solution so extreme it initially sounded impossible. He suggested the universe experienced a brief episode of exponential expansion shortly after cosmic expansion began, between roughly 10 to the negative 36 seconds and 10 to the negative 32 seconds. The interval was unimaginably brief, but during that tiny fraction of a second, space expanded by at least 10 to the 26 times its original size. A region smaller than a proton became large enough to contain everything we can currently observe. Guth called this process inflation. The mechanism depended on a hypothetical scalar field called the inflaton. A scalar field simply means a field with magnitude, but no direction, spread throughout space itself. While the inflaton carried high energy, it forced spacetime to expand at extraordinary speed. Suddenly the puzzles aligned. Before inflation, the entire observable universe occupied a tiny connected region where heat and radiation could mix freely. That explained the uniform temperature we still observe today. Inflation then stretched that once connected patch across immense distances. The flatness problem disappeared too. Rapid expansion smoothed curvature the way enlarging a tiny curved surface makes it appear straighter locally. Any magnetic monopoles became diluted so completely that finding one today became extremely unlikely. Eventually, the inflaton field decayed. Its stored energy converted into matter and radiation through a process called reheating, creating the hot, dense state traditionally associated with the Big Bang. But inflation changed something even larger than the early universe. It implied our observable region may be only a microscopic fragment of a vastly greater cosmos, extending far beyond every horizon we will ever see, perhaps without any meaningful boundary at all. Before stars existed, before galaxies spiraled across darkness, the universe resembled a furnace without windows. Matter and light were trapped together inside a dense, glowing plasma, a state where electrons moved too violently to remain attached to atomic nuclei. Nothing could travel freely. Every photon, the particle carrying light, scattered almost immediately after moving any meaningful distance. Space was opaque in every direction, not because it lacked light, but because it contained far too much of it. Then the temperature began to fall. Roughly 380,000 years after cosmic expansion began, the universe cooled enough for electrons to combine with protons and form stable hydrogen atoms for the first time. Cosmologists call this moment recombination. The effect was instantaneous on cosmic scales. Once electrons became bound inside atoms, photons stopped colliding constantly with charged particles. The fog lifted. Light suddenly moved freely across the universe, continuing outward for billions of years without interruption. That ancient light still surrounds us now. It arrives from every direction as the cosmic microwave background, usually shortened to the CMB. It is the oldest light we can ever observe because anything earlier remained trapped inside the primordial plasma. We are immersed within it. Today, the CMB measures about 2.725 Kelvin, only slightly above absolute zero, but when it first escaped, it glowed at thousands of degrees. The cooling happened because cosmic expansion stretched the wavelengths of the radiation itself, gradually transforming visible light into faint microwaves. Its discovery happened almost by accident. In 1965, radio astronomers Arno Penzias and Robert Wilson were working at Bell Labs with a giant horn antenna designed for satellite communications. They kept detecting a persistent background hiss that refused to disappear no matter where they pointed the instrument. They checked the equipment repeatedly. They searched for electronic interference. At one point, they even removed pigeon droppings from inside the antenna, suspecting contamination from nesting birds. But the signal remained perfectly uniform across the sky. What they had found was the leftover radiation from the young universe itself. But the CMB contained more than ancient light. Tiny fluctuations within it, temperature differences of roughly 1 part in 100,000, revealed slight density variations in the early plasma. Regions with slightly more matter possessed slightly stronger gravity, allowing them to attract additional material over time. Those tiny irregularities became everything. Galaxies formed there. Clusters emerged there. Even the immense cosmic voids began there. The pattern of those fluctuations also exposed the geometry of space itself. In positively curved space, the hot and cold regions would appear larger. In negatively curved space, they would appear smaller. The measurements matched flat geometry almost exactly. The Planck satellite, launched in 2009, mapped the CMB with extraordinary precision and found the universe remains flat within less than 0.5%. And in cosmology, a flat universe carries a profound implication. Space may continue forever, beyond the limits of what light has allowed us to see. Take 3 points in ordinary space and connect them into a triangle. Here on Earth, the angles add neatly to 180 degrees. We learn this in childhood and rarely question it because at human scales, space appears perfectly ordinary. But geometry changes when space itself curves. On the surface of Earth, which is positively curved, giant triangles behave differently. Imagine one line running from the equator to the North Pole, another returning to the equator 90 degrees away, and a third connecting them along the equator itself. The triangle now contains 3 right angles, 270 degrees total. Space can reshape geometry. Cosmologists realized that the universe as a whole could possess curvature too, and that curvature would determine whether space has an edge, whether it loops back on itself, and whether it extends forever. There are three basic possibilities. Positive curvature means space bends back onto itself like the surface of a sphere. Such a universe would be finite yet boundaryless. You could travel endlessly in one direction and eventually return to your starting point without ever crossing an edge. There would be no outside. Negative curvature behaves differently. Space curves outward like a saddle, causing parallel lines to diverge over enormous distances. Such geometry produces an open universe extending infinitely. Then there is flat geometry. Flat does not mean two-dimensional. It means Euclidean geometry remains valid across cosmic scales. Parallel lines stay parallel forever. Giant triangles still sum to 180 degrees no matter how large they become. This is the geometry observations seem to favor. Measurements of the cosmic microwave background, especially from the Planck satellite, show the universe remains flat within less than 0.5%. That result may sound abstract, but its implications are immense. If space is flat and its topology, meaning its overall connected structure, is simple, then the universe is almost certainly infinite. An infinite universe changes the expansion question completely. If space already extends without limit, there is no outer boundary pushing into emptiness. Expansion does not happen at some advancing frontier. New regions are not appearing at an edge because no edge exists. Every location already exists. The distances simply grow. Imagine an infinite rubber sheet covered with dots. Stretch the sheet, and every dot moves farther from every other dot. But there is no direction the sheet expands toward because the sheet never possessed a boundary to begin with. The stretching is internal. It belongs to the geometry itself. This becomes the first major answer to the question we have been carrying since the beginning. If the universe is spatially infinite, asking what it expands into may contain a hidden mistake. The question assumes expansion requires an exterior region waiting beyond the edge. But an infinite cosmos has no frontier, no surrounding emptiness, no outer wall, only changing distances embedded within the structure of space itself. And this is where intuition begins to fail us. Human minds evolved to track objects moving through environments, animals crossing landscapes, stones falling through air, rivers flowing across terrain. We instinctively imagine growth as something requiring room around it. But cosmology asks us to picture space itself as the thing changing, with no external stage beyond it at all. By the late 1990s, astronomers believed they understood the broad fate of cosmic expansion. The universe had begun expanding long ago. Gravity was pulling against that expansion, and the only remaining question seemed straightforward. How quickly was the expansion slowing down? Nobody expected the answer to overturn cosmology. Two competing research teams set out to measure the deceleration directly. One was the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. The other was the Supernova Cosmology Project, led by Saul Perlmutter. Their method relied on Type 1, a supernovae, stellar explosions produced when white dwarf stars accumulate too much mass and collapse catastrophically. These explosions release nearly identical intrinsic brightness every time, making them reliable standard candles. If you know how bright something truly is, comparing that value to how dim it appears reveals its distance. The teams searched deep into space and far back through time. They expected distant supernovae to appear slightly brighter than predicted because gravity should have slowed expansion over billions of years, leaving those galaxies closer to us than a steadily expanding universe would suggest. But the supernovae looked dimmer, farther away. The implication was immediate and deeply unsettling. Expansion was not slowing down at all. It was accelerating. The farther astronomers looked into the universe, the more strongly the data pointed toward the same impossible conclusion. Some unknown influence was pushing space-time apart faster and faster over time. Neither team trusted the result at first. Both spent months checking calibration errors, telescope sensitivity, dust contamination, and statistical mistakes. The measurements survived every test. In 1998, both groups published their conclusions independently. The universe was expanding at an increasing rate, driven by something entirely unexpected. Physicists named it dark energy. The phrase sounds descriptive, but it is really an admission of ignorance. Dark energy simply refers to whatever causes cosmic acceleration. No one knows what it fundamentally is, yet its effects dominate the cosmos. Current measurements suggest roughly 68% of the universe consists of dark energy. About 27% is dark matter, the invisible gravitational substance shaping galaxies and clusters. Everything familiar, stars, planets, gas clouds, oceans, trees, and human beings, accounts for only about 5%. Most of reality is unknown. Then came an extraordinary historical twist. Einstein's old cosmological constant, the mathematical term he introduced decades earlier to prevent cosmic expansion, suddenly returned to relevance. His equations naturally allowed empty space itself to possess energy. Einstein removed that possibility because he wanted a static universe. But the universe appears to have restored it. If dark energy behaves like a constant energy density embedded within empty space, then expansion will continue accelerating indefinitely. Galaxies outside our local gravitational neighborhood will drift away faster and faster as spacetime stretches between them. Eventually, the separation becomes irreversible. Light emitted from distant galaxies will never reach us again because expansion will outpace its ability to cross the growing gulf. One by one, entire galactic systems will disappear beyond the observable horizon permanently. The expansion of the universe is therefore not only changing distances, it is gradually reducing the amount of cosmos any future civilization will ever be able to see. Light travels at roughly 300,000 kilometers per second through empty space. According to relativity, nothing carrying information can move through spacetime faster than that limit. But spacetime itself follows different rules. This distinction feels subtle at first, yet it changes how we understand the observable universe completely. Galaxies are not merely drifting through a static cosmic backdrop. The fabric between galaxies is expanding, and that expansion is not constrained by the speed of light. Right now, countless galaxies are receding from us faster than light itself. Not because they are breaking relativity, because the space separating us grows too quickly for light to overcome. Cosmologists describe one important threshold using the Hubble radius, currently around 14.4 billion light-years away. At that distance, recession velocity equals the speed of light. Beyond it, galaxies recede superluminally, meaning faster than light due to expansion. And yet, we can still observe many of them. That seems impossible at first, but the explanation lies in timing. The light reaching Earth today left those galaxies billions of years ago, when they were much closer, and the expansion rate between us was smaller. Those photons began their journey while the cosmic river was narrower. Then the river widened beneath them. Some photons still continued making progress toward us despite expansion, constantly stretching the intervening space. Others never arrived at all. This leads to a deeper boundary called the cosmic event horizon currently estimated around 16 billion light years away. Unlike the observable horizon, which marks how far past light has already reached us, the event horizon marks the limit beyond which light emitted today will never arrive in the future. Ever. Any galaxy currently beyond that distance has already become permanently unreachable in a physical sense. Even if humanity survived for trillions of years, no signal sent from those galaxies right now could ever cross the expanding gulf separating us. But the process continues gradually. Galaxies presently visible beyond the event horizon still appear in our telescopes because we are receiving ancient light emitted long ago. Over immense spans of time, that remaining light will stretch toward longer and longer wavelengths until the galaxies fade entirely from view. The sky will slowly empty itself. In roughly 150 billion years, every galaxy outside the local group will have disappeared permanently beyond the cosmic horizon. The Milky Way and Andromeda, already moving toward collision, will merge into a single giant galaxy surrounded by darkness. Future astronomers born then will see almost nothing beyond their local stars. No distant galaxies, no cosmic microwave background, no visible evidence that cosmic expansion or the Big Bang ever occurred. They may conclude the universe is static and eternal because the information proving otherwise will be gone. This means we occupy a strangely privileged moment in cosmic history. The universe remains old enough for structure to exist, yet young enough that its origins are still visible across the sky. But the window is closing continuously. Expansion is not merely increasing distances between galaxies, it is gradually erasing the observable memory of the cosmos itself, carrying entire regions beyond the reach of every future observer who will ever exist. For most of human history, space seemed passive, empty, silent, a vast container where planets moved, stars burned, and galaxies drifted without affecting the stage beneath them. Isaac Newton formalized that picture in the 17th century. In his framework, space existed independently of matter and time. It stretched infinitely in all directions, perfectly rigid and completely unaffected by whatever happened inside it. Events unfolded within space. Space itself did nothing. That idea survived for centuries because it matched ordinary experience. Rooms remain still while people move through them. Landscapes do not bend when birds cross the sky. Empty space appears detached from the objects inside it. But Einstein overturned that intuition completely. In 1915, he published General Relativity, a theory describing gravity not as a force pulling objects together across emptiness, but as geometry itself. Space and time fused into a single four-dimensional structure called spacetime, a dynamic fabric capable of changing shape. Spacetime could bend, stretch, ripple. Matter no longer moved through a passive background. Matter altered the geometry around it, and that altered geometry guided motion in return. The Earth, for example, does not secretly pull the moon with invisible strings. Instead, Earth curves the spacetime surrounding it. The moon follows the straightest available path through that curved geometry, creating what we perceive as an orbit. Gravity became shape. This was one of the deepest conceptual shifts in scientific history because it transformed space from a container into a physical participant in reality. The famous rubber sheet analogy tries to visualize this idea. Place a heavy ball on a stretched sheet, and the surface curves downward. Smaller balls rolling nearby spiral inward because the geometry beneath them has changed. The analogy helps, but it also hides something important. The rubber sheet rests inside a larger room. Real spacetime does not. General relativity contains no external environment holding spacetime up from the outside. The geometry simply exists on its own terms. There is no deeper stage beneath it. This became even more concrete in September 2015 when the Laser Interferometer Gravitational Wave Observatory, known as LIGO, directly detected gravitational waves for the first time. These waves originated from two colliding black holes, roughly 1.3 billion light years away. The collision disturbed spacetime itself. Ripples spread outward across the universe at light speed, slightly stretching and compressing space as they passed through Earth. LIGO measured distortions smaller than the width of a proton. Space-time behaved like a physical medium capable of carrying waves, something real, something dynamic. And this returns us directly to the question we have been following since the beginning. In general relativity, spacetime does not require an external container because the theory defines all geometry internally. The equations describe how matter, energy, distance, and curvature relate to one another entirely within spacetime itself. There is no mathematical term for a surrounding void outside the universe because the framework has no need for one. That absence matters profoundly. The expansion of the universe is therefore not objects rushing outward through pre existing emptiness. It is spacetime itself evolving geometrically, changing the distances between galaxies without moving through anything beyond itself at all. At the deepest level, cosmology eventually becomes an exercise in measurement, not measuring stars or galaxies directly, but measuring the geometry connecting every point in the universe across time. For that task, physicists use something called a metric. A metric is simply a mathematical rule for calculating distance. On Earth, geometry tells you how far two cities are separated across a curved surface. In cosmology, the challenge becomes far stranger because the distances themselves evolve while the universe expands. During the 1920s and 1930s, Alexander Friedman, Georges Lemaitre, Howard Robertson, and Arthur Walker independently developed the mathematical framework now called the FLRW metric, short for Friedman, Lemaitre, Robertson, Walker. The equation assumes two large-scale properties: homogeneity, meaning the universe looks statistically similar in every location, and isotropy, meaning it looks statistically similar in every direction. Not perfectly identical everywhere, of course. Galaxies cluster, stars form, black holes emerge. But averaged across enormous distances, the cosmos behaves with remarkable uniformity. Inside the FLRW metric sits one crucial quantity called the scale factor, written as a cosmic of t. The symbol represents how cosmic distances change with time. It is deceptively simple. At extremely early times, the scale factor approaches zero, meaning all distances shrink toward nothing. By convention, cosmologists define the present universe so that the scale factor equals 1 today. In the future, if expansion continues, the value becomes larger than 1. Every distance grows proportionally. But this growth does not happen because galaxies accelerate through fixed emptiness like spacecraft leaving a launch site. The galaxies can remain stationary within their coordinate system, while physical distance still increases between them. Space itself changes scale. Imagine 2 points painted onto an elastic surface. If the surface stretches, the points separate despite never moving across the material beneath them. Their coordinates remain fixed while the geometry expands. The FLRW metric formalizes exactly this behavior mathematically. And something extraordinary appears once you examine the equation carefully. There is no variable representing an exterior region surrounding spacetime, no coordinate outside the geometry, no higher dimensional container where expansion takes place. The mathematics is entirely self contained. This becomes the rigorous scientific answer to the question we have been following from the beginning. In modern cosmology, saying the universe expands simply means the scale factor increases over time. That is the phenomenon. Nothing inside the equation describes expansion into another space because the equation models space itself, not motion through something external. The changing geometry requires no surrounding environment any more than the surface of Earth requires a second surface beneath it to define latitude and longitude. But this answer rarely feels emotionally satisfying at first encounter. Human intuition insists that anything growing larger must occupy additional room somewhere. We instinctively search for an exterior because ordinary experience trained us to think that way. Houses expand into land. Smoke expands into air. Water spreads across surfaces. Yet the FLRW metric quietly removes the exterior entirely. The geometry evolves internally, distances changing everywhere at once, without any frontier advancing into emptiness beyond the universe itself. Two spaces can share the same geometry while possessing completely different overall structures. This sounds impossible at first, but topology, the study of how space connects globally, allows realities that local measurements alone cannot reveal. Geometry tells you how space curves nearby. Topology tells you where space ultimately leads. A flat universe, for example, may still behave in radically different ways depending on its topology. The simplest possibility is an infinite universe extending forever in all directions, with no edge and no repetition. This is the standard assumption in most cosmological models, but it is not the only possibility. Imagine an old arcade game where a spaceship exits the right side of the screen and instantly reappears on the left. Travel upward, and the ship returns from below. The visible area remains flat, yet the space loops back on itself seamlessly. Mathematicians call this structure a torus. In two dimensions, it resembles the surface of a donut, but the idea extends into higher dimensions as well. A three-dimensional toroidal universe could remain perfectly flat locally while still being finite overall. You would never encounter a wall. No edge would appear. Instead, traveling far enough in one direction could eventually bring you back to your starting point from the opposite side, even though space itself remained geometrically flat throughout the journey. This possibility changes the expansion question again. A finite toroidal universe requires no external room to grow because its geometry closes internally. Expansion would simply increase distances everywhere within the connected structure itself, much like enlarging a seamless grid without introducing any surrounding environment. No outside becomes necessary. And unlike simpler visual analogies, this picture avoids implying some hidden interior region surrounding the universe physically. The connectivity belongs entirely to space itself. But how could we ever test such an idea? Cosmologists realized the cosmic microwave background might preserve clues. If the universe loops back on scales smaller than the observable horizon, light from the same ancient regions could reach us along multiple paths. That would produce matching circular patterns in different parts of the microwave sky. The same fluctuations repeated twice. The Planck collaboration searched carefully for those signatures, using the most detailed CMB maps ever constructed. No convincing matched circles appeared. At first glance, This seems to favor infinite space, but the conclusion is more subtle. The absence of repeated patterns only tells us that if space loops back on itself, the scale must exceed the observable universe itself. And that creates a permanent limitation. If the topology scale lies beyond our cosmic horizon, no observation can ever confirm whether the universe is truly infinite or merely extremely large and closed. Light from the repeated regions would simply never have enough time to reach us. This becomes one of cosmology's strangest boundaries. The universe may possess an elegant global structure hidden forever beyond observation, not because our instruments lack power, but because spacetime itself prevents access to the evidence. We can measure local geometry with extraordinary precision, but the full shape of existence may remain permanently out of reach, concealed beyond the finite sphere of information surrounding every observer in the cosmos. A soap bubble forming inside boiling water lasts only a moment. It appears suddenly, expands, separates from the liquid around it, then drifts away as its own distinct region. Some cosmologists believe our universe may have begun in a strangely similar way. The original inflationary model described a brief episode. Space expanded exponentially for a tiny fraction of a second. The inflaton field decayed, and ordinary cosmic evolution began. Clean, temporary, finished. But the equations refused to stay that simple. As physicists explored inflation more deeply during the 1980s and 1990s, many versions of the theory produced a disturbing result automatically. Inflation did not end everywhere simultaneously. Quantum fluctuations, tiny random variations arising from uncertainty at microscopic scales, caused different regions of space to evolve differently over time. Some regions stopped inflating, others continued, and the inflating regions expanded so rapidly that they always generated more volume than was lost when inflation ended locally. Even as countless bubble universes formed, the surrounding inflating background kept growing faster than those bubbles could consume it. Inflation became eternal. In this picture, our observable universe occupies one localized bubble where inflation ended long ago. Inside that bubble, matter condensed, stars formed, galaxies emerged, and cosmic history unfolded much as we have already described. But beyond our horizon, inflation may still continue endlessly. Other bubbles would constantly appear elsewhere inside the inflating background, each separated from the others by distances expanding faster than light could ever cross. These regions would remain permanently causally disconnected, meaning no signal, particle, or information could travel between them. Entire universes isolated forever. The implications become even stranger once string theory enters the picture. In many models, the inflaton field can decay into different vacuum states, each producing different physical constants. One bubble universe might possess stronger gravity, another might contain heavier electrons or a larger cosmological constant. Some universes could collapse instantly, others might never form stars. A few rare regions could allow complexity and life. This enormous collection of possible universes is sometimes called the landscape, a vast range of physical realities generated from different underlying conditions. At first glance, eternal inflation appears to answer the question we have been pursuing. It seems to place our universe inside something larger, an inflating background from which bubbles emerge. But the situation remains subtler than that. Our universe does not expand outward into the surrounding, inflating space the way smoke expands into air. The boundary separating our bubble from the exterior behaves more like an event horizon, a causal limit beyond which communication becomes impossible. The outside cannot influence us. We cannot influence it. For every practical purpose, the exterior remains unreachable forever. This creates one of the strangest situations in modern physics. Eternal inflation emerges naturally from respected mathematics and connects elegantly with several major theories. Yet its larger structure may never become directly testable because all evidence beyond our bubble remains permanently inaccessible. Even here, with universes potentially blooming endlessly beyond our horizon, the expansion we observe stays internal to our own spacetime region. The surrounding background exists mathematically, perhaps physically, but observationally it may as well be infinitely far away. A violin string vibrates differently to produce different musical notes. One frequency creates a low tone, another produces a higher pitch. String theory begins with a strangely similar idea, except the vibrating objects are unimaginably small and the notes become particles. Electrons, quarks, photons, even gravity itself. According to string theory, these particles are not truly separate objects. They are different vibrational states of tiny, one-dimensional strings of energy, smaller than anything current experiments can directly observe. The idea emerged gradually during the late 20th century as physicists searched for a way to unite quantum mechanics with gravity. Standard particle theories treated particles as mathematical points, but those equations generated infinities once gravity entered the picture. Strings softened the mathematics. The infinities disappeared. But the solution came with an extraordinary cost. For the equations to remain internally consistent, the universe required more dimensions than the familiar three of space and one of time. Far more. Most versions of string theory demand 10 spacetime dimensions. M theory, developed during the 1990s as a broader, unifying framework, requires 11. The additional dimensions would be curled into tiny geometric structures, far smaller than atomic nuclei, hidden from ordinary perception. Inside M theory, strings are not the only fundamental objects. The mathematics also allows higher dimensional membranes, called branes. That word changes everything. In brain world cosmology, our entire observable universe may exist on a three-dimensional brain floating inside a higher dimensional bulk space. Every particle, every star, every galaxy, every atom in your body would remain confined to this brain the way ink remains trapped on a sheet of paper. Only gravity could move through the larger bulk. Suddenly, the expansion question gains a radically different answer. In these models, the universe really is embedded within something larger, not metaphorically, literally. This possibility became especially influential after 1999 when physicists Lisa Randall and Raman Sundram proposed specific brain world models involving a five-dimensional bulk geometry. Their work offered potential explanations for one long-standing mystery: why gravity appears dramatically weaker than the other fundamental forces. If gravity partially leaks into higher dimensions, its apparent weakness inside our brain begins to make sense. Physicists searched for evidence carefully. Newton's inverse square law predicts how gravity weakens with distance. Brainworld models suggested deviations might appear at microscopic scales if extra dimensions existed nearby. Experiments tested gravity down to roughly 56 micrometers. No deviation appeared. If higher dimensions exist, they remain hidden below that threshold. But some brain world ideas became even stranger. In 2001, Paul Steinhardt and Neil Turok proposed the ekpyrotic model, where the Big Bang resulted from a collision between enormous brains drifting through higher dimensional space. The collision released vast energy. Expansion followed. Cosmic history began. In these scenarios, the universe truly expands within a larger environment, yet the bulk space surrounding our brain would obey unfamiliar geometry and inaccessible physics. Light, matter, and information remain trapped inside our cosmic membrane. We could never step outside it. Even if the universe exists inside something larger, after all, the surrounding reality may remain permanently invisible, separated from us not by distance, but by the deeper structure of spacetime itself. Imagine removing everything from a region of space, every atom, every photon, every trace of gas and dust. Cool the region to absolute zero, the coldest temperature physically possible, where molecular motion nearly stops entirely. Classical physics would say nothing remains, a perfect void. But quantum mechanics gives a completely different answer. Even the emptiest possible vacuum still churns with microscopic activity. Beneath apparent stillness lies a fluctuating quantum state filled with temporary energy and restless uncertainty. Empty space refuses to stay empty. This behavior emerges from the Heisenberg uncertainty principle, one of the central rules of quantum physics. The principle states that certain pairs of physical quantities cannot both be known with perfect precision simultaneously. One version involves energy and time. The shorter the time scale, the less precisely energy must behave. That uncertainty allows tiny fluctuations to appear spontaneously inside the vacuum itself. Particle-antiparticle pairs briefly emerge, exist for unimaginably small fractions of a second, then annihilate each other again before direct observation becomes possible. These are called virtual particles. They sound abstract, but their effects are measurable. One famous example is the Casimir effect, predicted in 1948 by Dutch physicist Hendrik Casimir. Place two uncharged metal plates extremely close together inside a vacuum. Quantum fluctuations between the plates become restricted because only certain wavelengths fit within the narrow gap. Outside the plates, fluctuations remain unrestricted. This imbalance creates a tiny inward pressure that pushes the plates together. The vacuum itself generates the force. Experiments repeatedly confirmed the effect with remarkable precision. Nothingness exerts pressure. Another demonstration emerged through the Lamb shift, measured by physicist Willis Lamb in 1947. Quantum vacuum fluctuations subtly alter the energy levels inside hydrogen atoms, slightly shifting the frequencies of emitted light. The effect was tiny, but real, and it matched quantum predictions exactly. By the late 20th century, physicists realized something even stranger. Quantum field theory predicts that the vacuum should contain enormous energy density, possibly as high as 10 to the 113 joules per cubic meter, depending on the calculation method. But astronomical observations tell a vastly different story. The observed energy associated with dark energy, the driver of cosmic acceleration, corresponds to roughly 10 to the minus 9 joules per cubic meter. The discrepancy between theory and observation spans approximately 122 orders of magnitude. It is the largest mismatch in all of modern science. No existing theory explains it successfully. Yet the connection to cosmic expansion remains unavoidable. Dark energy may ultimately arise from vacuum energy itself, meaning empty space possesses an intrinsic tendency to drive space-time outward as the universe evolves. If that idea proves correct, then expansion is not caused by some external pressure, pushing galaxies apart from beyond the universe. The process originates internally from the quantum structure of spacetime itself. The vacuum becomes active, creative, dynamic. What appears empty at human scales transforms into one of the most energetic and mysterious ingredients in existence, a hidden sea of fluctuating fields, quietly shaping the fate of the cosmos from within the fabric of space itself. The phrase Big Bang creates an image almost instantly. A brilliant fireball erupts from a single point, blasting outward into darkness like a cosmic detonation. The image feels natural, and almost every part of it is wrong. Explosions happen inside space. A bomb expands into surrounding air. A supernova expands into the interstellar medium around a star. Every explosion you have ever seen involved material moving outward through a pre existing environment. The Big Bang did not. There was no empty cosmic room waiting beforehand. According to general relativity, space itself emerged alongside the early universe. The expansion was not matter, flying into emptiness. It was the rapid growth of space-time itself. No external void existed. That also means the Big Bang had no center. This is one of the hardest ideas for human intuition to accept because every ordinary explosion begins from a specific location. But in cosmology, every observer sees distant galaxies receding in all directions regardless of where they stand. Every region appears central, not because we occupy a privileged position, but because the expansion occurs everywhere simultaneously. The Big Bang was not an event at one point inside the universe. It was an event involving the universe as a whole. More precisely, the early universe and the Big Bang are the same thing viewed at different moments in cosmic time. There was also no outward direction. Directions exist only inside space: north, south, left, right, above, below. These are relationships defined internally within geometry itself. If spacetime expands everywhere at once, there is no external direction into which it grows. All directions remain contained within the expansion. The confusion deepens near the beginning itself. If we mathematically rewind the FLRW equations backward through time, the scale factor approaches zero. Density and temperature rise toward infinity. This state is called a singularity, but physicists do not interpret this literally. A singularity marks the breakdown of the equations, not necessarily the breakdown of reality itself. It signals that general relativity becomes incomplete under such extreme conditions. Quantum effects almost certainly dominate there, yet no successful theory fully combines gravity and quantum mechanics. The mathematics stops functioning cleanly. Our understanding stops with it. What cosmologists actually mean by the Big Bang is far narrower and more precise than popular imagination suggests. The term describes the hot, dense, rapidly expanding early state from which our current physical laws successfully describe cosmic evolution. It does not necessarily describe the ultimate beginning of existence. And this reveals another hidden assumption inside one of the oldest questions people ask: what was the universe expanding into before the Big Bang? The sentence assumes time already existed before expansion began. But according to relativity, time itself may have emerged alongside spacetime. No earlier moment may exist physically. In that case, asking what happened before the Big Bang resembles asking what lies north of the North Pole. The question sounds meaningful grammatically, yet the underlying framework no longer supports the concept being requested. This is not avoidance. It is the edge of what current physics can honestly say about the beginning of the universe and the structure of time itself. A beginning feels simple in ordinary life. A song begins, a storm begins, a human life begins. Every event arrives after something else, positioned along a river of time that seems permanent and external to whatever happens inside it. Classical physics shared that assumption. In Newton's universe, time flowed independently of matter, endlessly and uniformly. Even if every star vanished, time itself would continue passing unchanged. Under that framework, asking what existed before the universe makes perfect sense because time already exists as the stage where events unfold. But relativity changed the stage itself. Einstein showed that time is woven into spacetime alongside the three dimensions of space. It bends near massive objects. It slows under gravity. Motion changes its rate. Time is no longer external to the universe. It is one of the universe's physical properties. That shift transforms the meaning of cosmic beginnings. If spacetime emerged with the early universe, then time may not extend infinitely backward beyond the Big Bang. There may be no earlier moment waiting behind it. In 1983, Stephen Hawking and James Hartle proposed one of the most famous attempts to formalize this idea mathematically. Their no boundary proposal applied quantum mechanics directly to spacetime geometry itself. The result was deeply strange. Near the earliest phase of the universe, the distinction between time and space begins to dissolve. Time gradually behaves more like another spatial dimension. Instead of encountering a sharp beginning, a hard edge where physics abruptly stops, the geometry curves smoothly into itself. No singular starting point appears. No temporal wall exists. Hawking compared this to Earth's surface. The North Pole marks a limit to northern travel, yet it is not an edge or boundary where the planet suddenly ends. Asking what lies north of the North Pole fails because the concept of north loses meaning there. The proposal suggests something similar for the Big Bang. If time itself fades away near the beginning, asking what happened before may become mathematically meaningless rather than merely unanswered. Surprisingly, a related intuition appeared long before modern physics. In the 4th century, Augustine of Hippo considered what God might have been doing before creating the universe. His conclusion was radical for the era. The universe, he argued, was created with time, not inside time. 15 centuries later, relativity moved strangely close to that idea. Not every cosmologist agrees with the no-boundary model, however. Roger Penrose proposed a different framework called conformal cyclic cosmology. In his picture, the universe passes through endless eons. After unimaginable spans of time, black holes evaporate, matter decays, and only radiation remains. At that stage, scale itself loses meaning. The cold, dilute future becomes mathematically equivalent to a new Big Bang. One cosmic era transitions into another without a final ending or absolute beginning. Penrose argued that faint traces of previous eons might still linger inside the cosmic microwave background, though the evidence remains disputed. Yet, both frameworks point toward the same unsettling conclusion. The question of what came before the universe may fail for the same reason asking, what lies north of the North Pole, fails. The structure supporting the question disappears at the boundary itself. Modern cosmology rests on a framework called lambda cold dark matter, usually shortened to lambda CDM. The name sounds technical, almost sterile, yet it represents one of the most successful scientific models ever constructed. Lambda refers to dark energy. Cold dark matter refers to the invisible matter shaping galaxies through gravity. Using only 6 primary parameters, the model predicts the large-scale structure of the universe with astonishing precision. It explains the cosmic microwave background, galaxy clustering, primordial element abundances, and the overall history of expansion remarkably well. For decades, it appeared secure. Then the numbers stopped agreeing. The problem centers on the Hubble constant, the present expansion rate of the universe. One method measures this value using the early universe itself. The Planck satellite studied tiny fluctuations in the cosmic microwave background, light emitted roughly 380,000 years after the Big Bang, using lambda CDM to evolve those early conditions forward through time gives a Hubble constant near 67.4 kilometers per second per megaparsec. A megaparsec equals roughly 3.26 million light years, but astronomers measuring expansion directly in the nearby universe obtain a different answer. The SH0ES collaboration, led by Adam Riess, used Cepheid variable stars and Type 1, a supernovae, to calculate cosmic distances independently. Their result approaches 73 kilometers per second per megaparsec. The disagreement seems small at first glance. It is not. The two measurements differ by more than 5 sigma, the statistical threshold physicists traditionally require before claiming a genuine discovery. At that level, random chance becomes extraordinarily unlikely. Something is wrong. For years, many researchers suspected hidden observational errors. Perhaps the nearby distance ladder contained unnoticed biases. But newer observations from the James Webb Space Telescope strengthened the local measurements rather than weakening them. The discrepancy survived. Both methods appear internally consistent, yet they predict different universes. This growing conflict is now called the Hubble tension, and it may represent the first serious crack in the modern cosmological model. If the tension proves real, then some ingredient inside lambda CDM remains incomplete or fundamentally incorrect. Several possible solutions exist. One proposal introduces early dark energy, an additional burst of repulsive energy present briefly in the young universe that altered the expansion rate before fading away. Another possibility involves dark matter interacting with itself or with radiation in previously unknown ways. Some physicists suspect general relativity itself may require modification across enormous cosmic distances. Others propose entirely new relativistic particles present shortly after the Big Bang. None of these ideas has been confirmed, but every serious solution changes our understanding of cosmic expansion itself. That matters deeply for the question we have been following throughout this journey. The expansion rate determines the age of the universe, the growth of structure, the behavior of dark energy, and the long-term fate of galaxies beyond our horizon. If lambda CDM eventually breaks, the deeper explanation for why space expands may change with it. The universe has done this before. Again and again, small discrepancies inside precise measurements opened hidden doors into entirely new physics. Mercury's orbit revealed relativity. Tiny spectral anomalies revealed quantum mechanics. Now another mismatch has appeared in the fabric of cosmology itself, quiet, persistent, and unresolved. A galaxy can appear calm from a distance. Spiral arms drift slowly through darkness, stars circling with quiet regularity across hundreds of thousands of light years. But when astronomers began measuring those motions carefully, the universe revealed a contradiction hiding inside nearly every galaxy ever observed. The stars were moving too fast. In the 1970s, Vera Rubin and Kent Ford studied spiral galaxies using sensitive spectrographs that separated starlight into precise wavelengths. By measuring tiny shifts in that light, They calculated how quickly stars orbited their galactic centers at different distances. Newtonian gravity made a clear prediction. Objects farther from the center should move more slowly because most visible mass lies near the middle. The outer planets in our solar system orbit more gradually than the inner ones for exactly this reason. But galaxies refused to behave. Stars near their outer edges moved almost as quickly as stars much closer inward. In many galaxies, the rotation curves remained nearly flat across enormous distances. Some outer stars even moved faster than expected. Visible matter alone could not explain it. If galaxies contained only stars, gas, dust, and black holes, many should have torn themselves apart long ago. Something unseen was providing additional gravity, holding these systems together like an invisible framework surrounding every luminous structure we observe. Astronomers named it dark matter. The term describes behavior rather than identity. Dark matter emits no light, absorbs no light, and appears completely invisible across the electromagnetic spectrum. We cannot photograph it directly because it does not interact with radiation the way ordinary matter does. Yet gravity exposes it everywhere. Each large galaxy appears embedded inside a massive dark halo, extending far beyond its visible disk. These halos outweigh ordinary matter by roughly 5 to 1. The Milky Way itself likely sits inside a dark matter halo spanning more than 1 million light years. But the evidence did not stop with galactic rotation. Gravity bends light itself, a phenomenon called gravitational lensing. Massive objects curve spacetime strongly enough to distort the paths of photons traveling nearby. Astronomers can therefore map invisible mass by observing how distant galaxies appear warped from Earth. One of the clearest examples emerged from the Bullet Cluster, two galaxy clusters that collided roughly 150 million years ago. The visible gas clouds slammed together and slowed dramatically, heating into bright X-ray plasma. The dominant mass did not stop. Lensing measurements showed most gravitational mass passed directly through the collision site, separating from the visible matter entirely. Whatever dark matter is, it behaves differently from ordinary atoms. Its fingerprints also appear in the cosmic microwave background. Tiny fluctuations in that ancient radiation contain a detailed statistical pattern called the power spectrum. The observed pattern only matches a universe containing about 27% dark matter. Without it, galaxies would have formed too slowly for stars and planets to exist today. Dark matter became the gravitational scaffold around which visible structure assembled. Yet, after decades of searching, physicists still do not know what it actually is. Proposed particles include WIMPs, axions, and sterile neutrinos, each predicted by theories extending beyond the standard model of particle physics. So the universe continues presenting us with the same unsettling truth. Most of the matter-shaping cosmic structure remains completely unseen. The long future of the universe depends on a quantity hidden deep inside dark energy, the mysterious component now driving cosmic expansion. Cosmologists describe it using the equation of state parameter, written as W, which compares the pressure of dark energy to its energy density. That single number changes everything. If W equals -1, dark energy behaves as a cosmological constant. The energy of empty space remains fixed even while the universe expands. Matter becomes more dilute across larger distances, but dark energy never weakens. Expansion accelerates forever. This is currently the best fit to observational data from supernovae, galaxy surveys, and the cosmic microwave background. It leads toward the scenario called the Big Freeze. Over immense spans of time, galaxies beyond the local group disappear permanently across the cosmic horizon. Their final photons stretch into wavelengths too long to detect. The observable universe slowly empties. Stars begin dying out. Within roughly 100 trillion years, most stars exhaust their hydrogen fuel. The smallest red dwarfs survive longest, glowing faintly for quadrillions of years before fading into darkness. White dwarfs cool. Neutron stars decay. Matter drifts through increasingly cold emptiness. Black holes dominate the late universe, but even they are temporary. In 1974, Stephen Hawking showed that black holes emit faint thermal radiation caused by quantum effects near their event horizons. Over timescales approaching 10 to the 100th years, even supermassive black holes evaporate completely. The universe approaches maximum entropy. Entropy means usable energy becoming evenly distributed. Temperature differences vanish. Structure disappears. Space-time becomes a dark, nearly featureless expanse, hovering just above absolute zero. But another possibility remains mathematically allowed. If W is less than -1, dark energy strengthens as space expands. Cosmologists call this phantom energy. Expansion accelerates without limit instead of remaining steady. This produces the Big Rip. Galaxy clusters separate first, then galaxies themselves unravel. Later, solar systems lose stability. Eventually, the expansion overwhelms molecular bonds, atomic structure, and finally, the strong nuclear force binding protons and neutrons together. Even space-time breaks apart. Some models predict this could occur within roughly 20 billion years. The final destruction would unfold in fractions of a second. There is also a third path. If W is greater than -1 and dark energy weakens over time, gravity could eventually slow the expansion. Galaxies would begin converging again across billions of years toward a final collapse called the Big Crunch. Some theories continue beyond collapse itself. Loop quantum cosmology proposes that quantum effects prevent a true singularity from forming. Instead, the collapsing universe rebounds in a big bounce, beginning another cycle of expansion with different conditions and another cosmic history. Each ending reshapes the meaning of expansion. In the Big Freeze, space stretches forever into increasing emptiness. In the Big Rip, expansion destroys the structures embedded inside spacetime. In cyclic models, expansion becomes one phase in an endless sequence of cosmic rebirths. At the center of many galaxies, including our own, something invisible controls the motion of entire star systems. Gas clouds accelerate around it. Stars whip through space at enormous speeds. Light itself bends around its gravity, yet nothing can be seen directly. Black holes are not strange objects added awkwardly onto physics. They emerge naturally from Einstein's equations when matter becomes compressed beyond a critical limit. Gravity overwhelms every known force resisting collapse. For the Sun, that limit is surprisingly small. If all solar mass were compressed into a sphere roughly 3 kilometers across, escape velocity would exceed the speed of light. A boundary would form around it called the event horizon. This boundary is often misunderstood. The event horizon is not a physical shell or solid surface. No wall exists there. It is a geometric feature of spacetime, a region beyond which every possible future path points inward. Once crossed, return becomes impossible because spacetime itself curves toward the center. An observer falling inward would notice nothing special at the horizon itself. But from far away, the picture changes dramatically. To an outside observer, The falling person appears to slow steadily as gravitational time dilation intensifies. Their light becomes redder, dimmer, and increasingly stretched until they seem frozen near the horizon forever. The similarity to cosmic horizons is difficult to ignore. Our observable universe also possesses a boundary defined not by matter but by information. Beyond the cosmic event horizon, light emitted today will never reach us because expansion stretches spacetime too rapidly. In a black hole, gravity traps information inward. In cosmology, expansion carries information outward, beyond reach. Both are horizons created by geometry. In 1974, Stephen Hawking revealed another extraordinary connection between gravity and quantum mechanics. Quantum fluctuations near the event horizon allow black holes to emit faint thermal radiation, now called Hawking radiation. Black holes slowly evaporate. A stellar mass black hole would survive for roughly 10 to the 67th years before disappearing completely. Supermassive black holes endure vastly longer, but according to current theory, none last forever. This leads directly into one of modern physics' deepest unresolved problems. Quantum mechanics states that information cannot truly vanish. Physical systems evolve predictably, even when transformed. But Hawking radiation appears completely thermal, containing no identifiable record of the matter that fell inward. So, what happens to the information? This conflict is called the black hole information paradox. It sits precisely where general relativity and quantum mechanics collide, the same frontier where our understanding of the early universe also fails. Deep inside a black hole, Einstein's equations predict a singularity. Density rises without limit. Space-time curvature becomes infinite. The mathematics breaks apart completely. The Big Bang contains the same failure. Our equations cannot fully describe what happens at the center of a black hole, just as they cannot fully describe the universe at its earliest moment. Both mark the edge of known physics, where gravity, quantum mechanics, space, and time cease behaving according to any framework we currently possess. Modern physics rests on two extraordinary frameworks, each tested with astonishing precision across its own domain. General relativity governs gravity, space-time, stars, galaxies, and the expansion of the universe. Quantum mechanics governs atoms, particles, radiation, and the invisible fluctuations underlying matter itself. Individually, both theories work beautifully, but together, they fail. At ordinary scales, this contradiction remains hidden. Quantum effects are negligible across galaxies, while gravity barely matters inside atomic systems. The two theories operate in different regimes, rarely forced into direct contact, but certain places refuse that separation. Inside black holes and near the beginning of the universe, gravity becomes immense at extremely tiny scales. Both relativity and quantum mechanics must apply simultaneously. When physicists combine the equations under these conditions, infinities appear everywhere. The mathematics collapses. This breakdown occurs near the Planck scale, the smallest meaningful scale currently known in physics. The Planck length measures roughly 10 to the minus 35th meters. The Planck time lasts about 10 to the minus 43rd seconds. Beyond this threshold, familiar intuition dissolves. General relativity describes space-time as smooth and continuous, like an unbroken fabric, but quantum mechanics predicts violent fluctuations at extremely small scales. Space itself may foam, twist, and fluctuate unpredictably. The geometry becomes uncertain. Physicists call the missing framework that unifies gravity with quantum mechanics quantum gravity. it remains one of the greatest unsolved problems in science. One major candidate is string theory. Instead of treating particles as dimensionless points, string theory proposes that every fundamental particle is a tiny vibrating string of energy. Different vibrational patterns produce different particles, including photons, electrons, and gravitons, the hypothetical quantum carriers of gravity. The theory naturally incorporates gravity, but it requires extra spatial dimensions beyond the familiar three. Most versions predict either 10 or 11 dimensions total, with the additional dimensions curled into scales far too small to observe directly. String theory is mathematically powerful, yet it remains experimentally unconfirmed. Current particle accelerators cannot reach energies high enough to test most predictions directly. Another approach moves in a different direction. Loop quantum gravity attempts to quantize spacetime itself. According to this framework, space is not continuous but granular, built from tiny discrete structures called spin networks. Time may also advance in fundamental increments rather than flowing smoothly. Continuity becomes an illusion. In some loop quantum gravity models, the Big Bang singularity disappears entirely. Instead of an infinite point of density, a previous contracting universe rebounds through a quantum bounce into expansion. No true beginning exists. Despite their differences, both approaches point toward the same unsettling possibility. The smooth spacetime described by relativity may not be fundamental at all. Space and time themselves could emerge from deeper, microscopic processes we do not yet understand. That possibility changes the expansion question profoundly. Our current answer, that the universe expands without expanding into anything external, comes from general relativity. But general relativity is incomplete. A future theory of quantum gravity may reveal that space-time itself emerges from something more basic, something where the distinction between inside, outside, before, and after no longer behaves the way human intuition expects. For most of human history, space seemed obvious. You could point to distance, direction, motion, emptiness. Space appeared to be the permanent stage beneath reality, something existing independently of whatever happened within it. Modern physics has begun to challenge that assumption. Some of the deepest ideas in theoretical physics now suggest that space may not be fundamental at all. It may emerge from something deeper, stranger, and more abstract than geometry. The first clues came from quantum entanglement. In quantum mechanics, entangled particles share linked properties regardless of separation. Measure one particle and the other responds instantly, even across enormous distances. Einstein disliked this implication intensely. In 1935, he called it spooky action at a distance. But experiments kept confirming it. Over time, physicists realized entanglement was not a rare curiosity. It appeared woven into the structure of quantum theory itself. More recently, researchers began noticing unexpected relationships between entanglement and spacetime geometry. The connection became sharper in 2013. Physicists Juan Maldacena and Leonard Susskind proposed the ER equals EPR conjecture. ER refers to Einstein-Rosen bridges, better known as wormholes. EPR refers to the Einstein-Podolsky-Rosen paradox, describing entanglement. The proposal was startling. Two entangled particles may be connected by microscopic wormholes. Entanglement and space-time geometry could represent different descriptions of the same underlying phenomenon. Distance itself might emerge from connectivity. This changes the meaning of space completely. Space would no longer be a fundamental container existing before matter and energy. Instead, Geometry would emerge from deeper quantum relationships, much like temperature emerges from the collective motion of molecules. Temperature feels fundamental to human experience, but a single molecule has no temperature. Temperature only appears statistically when enormous numbers of particles interact together. Some physicists suspect space behaves similarly. Another idea pushes this even further. The holographic principle proposes that all information contained within a three-dimensional region can be fully encoded on a two-dimensional boundary surrounding it. The concept emerged from black hole thermodynamics and later became central to string theory. Reality may function like a hologram. The most important realization of this principle is the ADS CFT correspondence, developed by Juan Maldacena in 1997. In this framework, a gravitational universe inside a curved spacetime is mathematically identical to a quantum theory without gravity living on its lower dimensional boundary. The interior geometry literally emerges from information. This duality has survived decades of mathematical testing. Many theoretical physicists now regard it as one of the strongest clues toward quantum gravity ever discovered. But its philosophical implications are extraordinary. If space emerges from quantum information, then expansion may not involve stretching a pre-existing arena at all. The universe would not expand into some external emptiness because spacetime itself would be continuously generated from deeper informational relationships. No underlying container exists. The container is part of the process. In that picture, asking what space expands into becomes similar to asking what a wave expands into inside an ocean. The wave is not separate from the water beneath it. Its existence is a dynamic pattern emerging from something deeper, something whose true nature we are only beginning to glimpse. Beneath every star, atom, and living cell sits a quiet layer of numbers. They do not describe particular galaxies or particles. They define reality itself. Modern physics depends on roughly 26 fundamental constants, fixed numerical values woven directly into the laws governing the universe. The speed of light, the strength of gravity, the charge of the electron, the masses of quarks, the energy density of empty space. No current theory predicts these values. We simply measure them. But physicists gradually realized something unsettling. Many of these numbers appear balanced within astonishingly narrow ranges. Alter them slightly, and the universe becomes sterile, long before life has any chance to emerge. Consider the strong nuclear force. This force binds protons and neutrons together inside atomic nuclei. Increase its strength by only about 2%, and nearly all hydrogen fuses into helium within minutes after the Big Bang. Stable hydrogen stars become impossible. Water disappears from cosmic history before planets even form. Reduce the force slightly instead, and fusion becomes inefficient. Carbon, oxygen, and nitrogen fail to emerge inside stars. The periodic table collapses into simplicity. No chemistry follows. The cosmological constant creates an even stranger problem. This constant governs the energy density of empty space itself, the same phenomenon associated with dark energy and cosmic acceleration. Observations show its value is tiny but positive, just enough to slowly accelerate expansion across billions of light years. But theoretical calculations from quantum field theory predict something catastrophic. The expected vacuum energy is approximately 10 to the 122nd power larger than what we actually observe. The mismatch is staggering. If the cosmological constant were only modestly larger, matter would never gather into galaxies. Gravity would lose the race against expansion almost immediately after the Big Bang. stars would never ignite. Space would thin into permanent darkness. Yet somehow, the value sits extraordinarily close to zero without being exactly zero. Physicists call this fine tuning. The numbers appear delicately arranged for complexity, not necessarily for life specifically, but for stable structures capable of producing chemistry, stars, planets, and long cosmic evolution. One response is called the anthropic principle. We observe a habitable universe because only habitable universes contain observers capable of asking the question. In sterile universes, nobody exists to notice the constants at all. This idea becomes more significant in eternal inflation models. If inflation continuously creates vast numbers of bubble universes, each potentially containing different physical constants, then most universes would remain lifeless forever. We would naturally appear in one of the rare exceptions. But many physicists remain dissatisfied with this answer. Selection effects explain why we observe compatible conditions, yet they do not explain why the underlying laws permit such a landscape in the first place. Another possibility remains open. The constants may eventually emerge from a deeper theory not yet discovered, a framework showing that these values are not arbitrary at all, but mathematically inevitable consequences of principles we still cannot see. For now, the numbers remain suspended between accident and necessity, delicate enough that every galaxy in the night sky depends upon them being almost exactly what they are. Numbers alone rarely feel real. You can hear the phrase billions of galaxies 100 times and still picture something manageable, something your mind quietly compresses into a familiar shape. But cosmology becomes different when you stop treating scale as vocabulary and begin treating it as distance. Start with home. The Milky Way is a barred spiral galaxy, approximately 100,000 light years across. Its disk contains somewhere between 100 billion and 400 billion stars. Our Sun drifts about 26,000 light years from the galactic center, orbiting once every 230 million years. A vast system already. Yet the Milky Way is only one galaxy among many nearby companions. Together we belong to the local group, a gravitationally bound collection of roughly 54 galaxies spread across nearly 10 million light years. Most are dwarfs. The dominant members are the Milky Way and Andromeda, both moving toward each other at about 110 kilometers per second. In roughly 4.5 billion years, they will merge into a larger elliptical galaxy while the broader expansion continues beyond them. But the local group is not isolated. It belongs to the Virgo supercluster, a structure spanning roughly 100 million light years and containing hundreds of galaxy groups and clusters connected through immense filaments of matter. For decades, astronomers thought this represented one of the universe's largest coherent structures. Then the map expanded again. In 2014, astronomer R. Brent Tully and his colleagues identified a still larger structure called Laniakea, meaning immense heaven in Hawaiian. Using galaxy velocity flows, they showed that the Virgo supercluster itself belongs to a larger gravitational basin, approximately 520 million light-years across. Its estimated mass equals 100 million billion suns. Yet even Laniakea is temporary. It is not fully gravitationally bound. Over immense timescales, dark energy will continue stretching the distances between its components until much of the structure dissolves beyond cosmic horizons. And still, we have barely begun. The observable universe measures approximately 93 billion light-years in diameter and likely contains around 2 trillion galaxies. Each galaxy contains billions or trillions of stars, many hosting planetary systems of their own. Human language starts failing here. Not poetically, literally. The numbers exceed intuitive cognition. Your brain evolved to track movement across forests and plains, not structures billions of light years wide. Even our metaphors collapse under the scale. But the observable universe may not be the whole universe. If space is flat and infinite, then no upper bound exists at all. Even if the universe is finite, with slight positive curvature below current detection limits, conservative estimates suggest the total volume could still exceed our observable region by factors around 10 to the 23rd power. That quantity resists imagination completely. And something changes when you sit with that honestly. The old intuition that the universe must be inside something larger begins to weaken, not because the equations force you to surrender it, but because the scale itself reshapes the question. The universe does not resemble an object floating in emptiness. It resembles the totality within which emptiness itself acquires meaning. The deeper we map the universe, the stranger the silence becomes. Astronomers now estimate that the observable universe contains roughly 2 trillion galaxies. Most contain hundreds of billions of stars. Around many of those stars orbit rocky planets, and a meaningful fraction appear to exist within habitable zones where liquid water could remain stable for billions of years. The raw numbers feel overwhelming. Given enough worlds and enough time, intelligence should not seem exceptional. Yet when we lift radio antennas toward the sky, the universe answers with quiet. This contradiction became known as the Fermi paradox. In 1950, physicist Enrico Fermi joined colleagues for lunch at Los Alamos National Laboratory. During the conversation, he suddenly asked a simple question. If intelligent civilizations are even moderately common, where is everybody? The mathematics behind the question remain uncomfortable. Even traveling at only 1% of light speed, a civilization could cross the Milky Way in roughly 10 million years. That sounds immense to us, but the galaxy itself is over 10 billion years old. Civilizations would not need to travel quickly. They would only need persistence. Over enough time, even slow expansion should spread technological life across enormous distances. Self-replicating probes alone could theoretically populate the galaxy within a tiny fraction of cosmic history. But we see no evidence. For more than 60 years, projects like SETI, the Allen Telescope Array, and Breakthrough Listen have scanned the sky for artificial signals. None have produced confirmed detections. The famous WOW signal recorded in 1977 lasted 72 seconds and never appeared again. The silence endured. Physicist Robin Hansen proposed one explanation in 1998. He called it the Great Filter. Somewhere between dead matter and galaxy-spanning civilizations lies a barrier so difficult that almost nothing passes through it. Perhaps simple life is extraordinarily rare. Perhaps intelligent life almost never emerges. Perhaps civilizations routinely destroy themselves through war, ecological collapse, artificial intelligence, or technologies we cannot yet imagine. We do not know where the filter lies. That uncertainty changes how we see the expansion itself. Dark energy is gradually isolating galaxies from one another. As cosmic acceleration increases, more regions slip permanently beyond reachable distance. The total number of accessible stars available to any civilization decreases over time. The universe was more connected in the past. It will become less connected in the future. A civilization emerging 1 trillion years from now would inherit a darker cosmos. Most galaxies will already have vanished beyond the cosmic horizon. Available matter, energy, and information will exist within far smaller islands of space. Opportunity itself is temporary. This possibility carries a strange implication. Intelligence may not merely arise within the universe. It may belong to a narrow cosmological era when galaxies remain visible, resources remain abundant, and the expansion has not yet sealed most of reality behind unreachable horizons. The silence above us may not mean the universe lacks minds. It may mean minds are brief. And while space continues expanding according to laws far larger than any civilization, every thinking species remains confined to a shrinking patch of reachable stars, watching the rest drift silently away into distances no signal will ever cross again. Every scientific instrument humanity has ever built shares the same dependency. Information must arrive. A telescope does not reach outward and touch distant galaxies. It waits for light. A detector does not penetrate reality directly. It records signals crossing space and time toward us. Every observation in cosmology depends on messengers that can physically reach Earth, and that condition creates permanent limits. The cosmic microwave background marks one of them. Before recombination, roughly 380,000 years after the Big Bang, the universe existed as an opaque plasma scattering light in every direction. Photons could not travel freely. The universe was fogged shut. When neutral atoms finally formed, light escaped and began its journey across expanding space. That ancient radiation became the cosmic microwave background, the oldest light we can observe. Nothing electromagnetic comes from earlier times. No matter how powerful future telescopes become, they cannot see beyond this surface of last scattering because no older light exists to collect. The limit is physical, not technological. Other boundaries are even deeper. The topology of the entire universe may remain forever hidden if its largest structures exceed our observable horizon. Space could loop back on itself at scales vastly beyond what light has had time to reveal. We may never know whether the cosmos is infinite or simply enormous beyond comprehension. But the horizon blocks certainty. The multiverse introduces another difficulty entirely. In eternal inflation models, other bubble universes would remain causally disconnected from ours forever. No signal crosses between them. No measurement can confirm their existence directly. At that point, cosmology approaches philosophy. The earliest moments of the Big Bang also remain concealed. The cosmic microwave background shows conditions hundreds of thousands of years after expansion began, not the beginning itself. Physicists hope primordial gravitational waves may someday probe closer to inflation, yet even those would not fully reveal the singularity where current equations collapse. Dark matter remains equally elusive. For decades, underground detectors, particle colliders, and astronomical surveys have searched for its identity across enormous ranges of mass and interaction strength. Nothing conclusive has appeared. We infer dark matter through gravity alone, like footprints crossing invisible ground. Dark energy may be worse. We can measure its effects with increasing precision while still lacking any confirmed understanding of what it physically is. The acceleration of cosmic expansion stands among the most important discoveries in modern science, yet its underlying mechanism remains obscure. But perhaps the deepest realization is this: some aspects of reality may not merely be unknown, they may be unknowable in principle. Information beyond cosmic horizons can never reach us. Regions outside our light cone remain permanently inaccessible, regardless of technological progress or intellectual effort. The universe may contain truths forever separated from observation. That possibility changes the emotional texture of science itself. Earlier generations often imagined ignorance as temporary, something steadily dissolved by better instruments and better theories. Cosmology suggests otherwise. It suggests there are edges, not just to exploration, but to knowability itself, boundaries built into spacetime long before minds evolved to wonder about them, long before Earth existed, before the sun ignited, before the Milky Way settled into its present spiral form. Generations of stars lived and died across the young universe. Inside those stars, atomic nuclei collided under immense pressure and temperature, building heavier elements from lighter ones. Carbon emerged there, oxygen too, the calcium in your bones, the nitrogen in your DNA, the iron moving through your bloodstream tonight all passed through stellar interiors billions of years ago. Supernova explosions scattered those elements into interstellar space, where gravity later gathered them into new stars, new planets, new chemistry. Eventually, one small world formed around an ordinary yellow star. And here you are. The universe is approximately 13.8 billion years old. Anatomically, modern humans have existed for roughly 300,000 years. Written civilization occupies only the last 5,000. Compared to cosmic history, all recorded memory fits into an interval so brief it almost disappears. Yet this tiny interval matters enormously. We exist during the stelliferous era, the age of stars, when matter still organizes itself into luminous structures and stable planetary systems. This period may continue for around 100 trillion years before stellar formation finally ends. We arrived near the beginning, but even now, the evidence of cosmic origins is slowly fading from view. The expansion of space continues stretching the cosmic microwave background toward longer wavelengths. Distant galaxies drift farther beyond the event horizon, each passing billion years. The universe is becoming harder to read. A civilization emerging 1 trillion years from now may inherit a dark and isolated cosmos. Most galaxies will already have vanished beyond observation. The microwave background may be stretched beyond detectability. The clues that allowed us to reconstruct cosmic history could disappear completely. They may never know the universe had a beginning at all. That realization changes the feeling of this moment. We often imagine ourselves as late arrivals standing near the end of discovery. Cosmology suggests something stranger. We may live unusually early, while the universe still preserves records of its own formation across the sky. We are temporary witnesses. The atoms composing your body have already existed in countless earlier forms, within collapsing gas clouds, ancient oceans, extinct organisms, and stars that burned out long before Earth formed. After your lifetime, those same atoms will continue again through new arrangements across the planet and beyond it. Matter persists, configurations change. And among all the known structures assembled from that ancient matter, one configuration learned to ask questions about existence itself. A network of neurons evolved on a small, rocky planet and became capable of wondering what space is, whether time had a beginning, and what the universe expands into. But perhaps the strangest part is this. The question is not separate from the cosmos that produced it. When you ask what lies beyond the expanding universe, the universe is examining its own structure through a temporary arrangement of atoms that can think, remember, and look outward into the dark. After all the equations, observations, satellites, particle theories, and thought experiments, we arrive at a conclusion that feels almost too simple for the scale of the question. The universe is not expanding into anything. Modern cosmology describes expansion through the Friedmann, Lemaitre, Robertson, Walker metric, usually shortened to FLRW. This framework treats spacetime itself as dynamic. Distances between galaxies increase because the geometry changes over time. Nothing needs to move outward. The scale factor, written as a T, grows continuously as the universe evolves. That single changing quantity describes the expansion completely within the mathematics of general relativity. No external coordinate appears anywhere in the equations. No outer region waits beyond the boundary of space. There is no boundary. If the universe is spatially infinite, then it was already infinite even during the earliest moments after inflation. Expansion does not add new territory onto an edge. Every distance simply stretches simultaneously across an already unbounded geometry. Infinity needs no container, but a finite universe changes very little about the answer. A positively curved or topologically closed cosmos can remain finite while still lacking edges. You could travel indefinitely without ever encountering a wall or exterior region, just as you can circle Earth endlessly without falling off its surface. The geometry closes on itself. Some modern approaches push even deeper. In holographic models and quantum gravity research, spacetime may not be fundamental at all. Space itself could emerge from relationships encoded within underlying quantum information. Distances and geometry may arise from entanglement patterns the way temperature emerges from molecular motion. In that picture, asking what space expands into becomes strangely misplaced. Space is not an object sitting somewhere larger. It is part of the process being generated moment by moment from a deeper structure we barely understand. But the difficulty of accepting this answer is important too. Human intuition evolved for forests, oceans, stones, storms, and moving animals across finite terrain. Every object we encounter grows within something else. Trees grow in soil. Smoke expands into air. Explosions move outward through surrounding space. Your brain expects containers because nearly every experience in human history involved containers. Cosmology breaks that instinct completely. The universe is not behaving strangely compared to ordinary objects. The universe is not an ordinary object at all. It includes the space in which all ordinary objects exist. That distinction matters. The discomfort many people feel when hearing this is not evidence that physics failed. It is evidence that human cognition was shaped at scales enormously smaller than the structure we are attempting to describe. And so the most honest conclusion remains careful and limited. We still do not know whether the cosmos is truly infinite, whether spacetime emerges from deeper physics, or whether future discoveries will revise the foundations of cosmology again. But across every observationally successful framework we possess today, one result remains remarkably consistent. The universe does not expand into an external space, because external space is not part of the universe's description in the first place. For a brief interval in cosmic history, the universe remains transparent enough for itself to be studied. The cosmic microwave background still surrounds us as a faint thermal glow, only 2.725 degrees above absolute zero. The large-scale web of galaxies still stretches across observable space. Hydrogen and helium still preserve the chemical ratios forged during the first minutes after the hot early universe cooled enough for nuclei to survive. The evidence is still here, but not forever. As expansion continues, distant galaxies recede beyond the cosmic horizon one by one, their final photons thin into darkness. The microwave background stretches toward wavelengths larger than galaxies themselves. Future observers may inherit a sky almost entirely empty, silent except for the dim remains of their own gravitationally bound systems. They may never know a beginning occurred. A civilization born trillions of years from now could reasonably conclude the cosmos is static and eternal. Without visible expansion, without background radiation, without access to primordial structure, the central discoveries of modern cosmology may become impossible to reconstruct. We happen to exist before that forgetting is complete. Not at the center of history, not at the climax of the universe, only early enough to still read the traces left across spacetime by processes unimaginably older than ourselves. A temporary species on a rocky planet developed radio telescopes, particle accelerators, detectors cooled near absolute zero, and mathematical tools capable of describing curved spacetime with astonishing precision. And through those tools, the universe became partially visible to itself. We learned that galaxies drift apart because space expands. We learned that time and geometry are linked. We learned that most of the cosmos consists of invisible matter and unknown energy. We learned that the observable universe spans 93 billion light years, while the total universe may extend infinitely beyond every horizon we can ever reach. But perhaps the strangest discovery is the simplest one. The universe does not appear to sit inside anything larger. It has no detected edge, no surrounding void, no external direction into which it expands. Space is not inside a container because space itself is the container within which all physical things exist. That answer feels almost impossible at first, yet the deeper we looked, the more consistently reality pointed there. Not toward hidden walls or external dimensions we could observe directly, but toward a cosmos whose geometry is self contained, dynamic, and sufficient unto itself. And still we continue asking. In a tiny patch of sky once photographed by the Hubble Space Telescope, smaller than a grain of sand held at arm's length, more than 10,000 galaxies shine across billions of years of time. Nearly every point of light contains hundreds of billions of stars. Around many of those stars, planets orbit in darkness. Somewhere among them, perhaps other minds are asking similar questions tonight. Not because the universe requires questioning minds, but because, against extraordinary odds, it produced them anyway.